Hi, this is Jiseong from Postec. It is a pleasure to present our mobility embedding project at HERE Network 2021. Let's talk about the mobility first. As we know, mobility is the origin of the innovations, economic development, and even epidemic disease at this stage. So understanding mobility is essential to understand a range of human phenomena and establish better policy. Then how can we study it? For studying mobility, gravity models have been used as a fundamental tool, and it is very powerful, intuitive tool which is motivated from the Newton's law of the gravity. In the gravity model, flux between location I and j, Tij is proportional to size of population of I and j, which is mi and mj, and decaying with the distance between two places. We can use any kind of distance measure for Rij, while geographical distance is popular choice. So the gravity model is effective, but geographical distance is not always appropriate. Let's think about this example. For instance, a person living in Australia is more likely to migrate to the United Kingdom, which is a faraway country but having similar language and cultures, than the much closer countries such as Indonesia. Similarly, a student in South Korea is more likely to attend a university in the United States than one in North Korea. Geography matters, but cultural, linguistic, economic, and even political distance are also important for studying current complex mobility. And here is our suggestions. How about the Runon embedding that captures the latent distance between the places directly extracted from the data? For this, we employ word-to-back method, which is designed from running representation of each word. Principle of the word-to-back is rather simple. A good representation allows predictions. Word-to-back text input as a sentence, and train a neural network to predict the target words given the context word, and use the result of the hidden layer as a representation of each word. But they don't have to be a real word or sentence. Any sentence, a sequence of elements, can be used. Let's imagine mobility of the scientist. You can use operation trajectory from the publication as a sentence and organization as a word. For this, we try to model mobility trajectory with constructing career trajectory of 3 million scientists derived from the publications and giving as input to word-to-back. Likewise, we can obtain the vector space representation of each organization, which can measure the functional distance between the pair of the organizations. Here is our first finding. Embedding distance outperforms geographical distance and offer a functional distance between the organizations. In here, plus Tij is the number of the time two organizations co-occur in the trajectories, and population Mi is the total number of the scientists of each organization. Because of the profs and population are given from the dataset, we can easily fit the gravity model using each distance measure in here. Upper figure uses the cosine distance of the embedding vectors as a distance measures, while bottom figure uses the geographical distance, and in here every point is a pair of the organizations. We found that flux strongly correlated with the embedding distance rather than geographical distance in terms of the high R scales, which means that embedding can offer a functional distance between the organizations. And using obtained gravity model, we can predict the flux between the organizations and compare with actual flux. Results suggest that embedding distance leads to better prediction with much smaller error of the predictions. Moreover, we found that our approaches perform well in other domains. We can get better similar results in the trajectory derived from the US domestic flights, and again for South Korean hotel reservation trajectories of the customers. And compared to other baselines such as a network-based approach or other matrix spectration approaches, our approach always outperforms other baseline metrics. The next question is that, why does it work so well? We found the answer from the mathematical equivalence between the word-to-back model and gravity models. Starting from the original conditional probability of the word-to-back, and considering negative sampling is a biased estimator, and we found that schistogram word-to-back with negative sampling is mathematically equivalent of the gravity model, and please check our preprint for the full derivations. Now, we could say word-to-back give off reasonable functional distance between the places and capture the latent structure of the mobilities. Then let's look into the what-if depth structure from the representations. From now, we're gonna focus on scientific mobilities and look into the geometric space generated by the neural embedding to understand complex relations between the organizations. For each organization embedding vectors, we can easily visualize an embedding space into the two-dimensional space with topology-based dimensional reduction method UMAP. In right figure, each dot represents organizations, and organizations tend to be from clusters based on their national affiliations, and national clusters tend to be near based on their geographical neighborhood. But we find various examples in here, for instance, organizations in Quebec and Montreal, which are French-speaking cities in Canada, are separate from the rest of Canada and located closer to the French cluster due to the language uses. We can also zoom in into the level of the country and state with simply applying UMAP on the subset of embedding vectors. For instance, in United States case, results reveal geographical clustering based on states, roughly grouped by census regions. And in the level of the state, we found clustering based on the urban centers in the states, organization sectors, for instance, hospital versus universities, and university systems like state university system and prestige. And just as embedding space makes it possible to zoom in on the subset of the organizations, but it is also possible to zoom out to figure out their high-level structures. We define the representative vector of each country with the average of their organization vectors, and using their cosine similarity, we perform hierarchical clustering of the nation with at least 25 organizations in the embedded spaces. We found 6 reasonable clusters roughly corresponds to countries in Asia and North America, North Europe, the British Commonwealth and Iran, Central and Eastern Europe, South America and Iberia, and Western Europe and Mediterranean. In Figure B, we demonstrate that geography plays a major role at higher level of the clustering process, and language or language family explain the clustering more at the low levels. It means that not only geography, but also linguistic and cultural ties between countries are related to the cluster structure of scientific mobility. And what else is encoded? In the word embedding, theme axis demonstrate that semantic axis can be founded from the embedding spaces by defining the pulse, and the latent semantic relations along the semantic axis can be extracted easily. For instance, we define gender axis from the subset of the pulse. Continuous gender spectrum of the pulse can be extracted from the embedding spaces with measuring cosine similarity between the embedding vectors of the pulse and gender axis. We try similar things with geography and prestige axis. Using 5 most and least prestigious universities in US based on Times Higher Education ranking as a whole, we can get prestige axis. And using our university in Massachusetts and California as a whole, we also can get the geography axis. In the same way, we project our university in the United States and obtain the continuous spectrum of universities in terms of the prestige and geography. We found that embedding space encodes the prestige hierarchy of the United States University, which is matched well with the real-world university ranking with high rank correlations. The embedding-based ranking is strongly correlated with timed ranking, and we could say theme axis reconstructs university prestige directly from the mobility trajectories. We also find that size of the organization vector provide insight into the characteristic of the organizations. In word embedding, words used in a single context tend to have a larger vectors for words like black holes, while the words that appear in more and more different contexts, words like the, have a shorter vectors, because they are more universal, more central. This also works for the organizations. Bigger organizations are more isolated unless they are prestigious. Those from prestigious universe are more central. We report that this curve is almost universal across many countries. For instance, China, Australia, Brazil exhibit similar curves to the United States. On the other hand, other nations exhibit different curves which reflect the portion with decreasing norms, probably indicating that lack of internationally prestigious organizations. In summary, here is our take-home message. We found that embedding captured the latent structure of the mobility from the underlying mathematical connection between the gravity model and word-to-back. Focusing on the scientific mobility, geography, language, culture, and prestige structure global scientific mobility. And we built that embedding-based approach can shed a light on deeper understanding of mobility across diverse domains. And this is the end of our presentation. Here's our awesome collaborators for this project, and our preprint can be accessed from this URL. Thank you for listening.